Okay, guys, let's continue with continuous distributions. And I'm going to begin with an example. F of x equals the absolute value of x, whose support for f is going to be defined as minus 2 to 3. So I can immediately draw a picture of what this function looks like. And without actually doing integration, I can demonstrate how to very quickly and easily determine the value of a, and that is it's 3 by 3, and so 2 by 2. So the integral under the absolute value of x from minus 2 to 3, well, it's area under the curve, so it's going to be 1/2 the base times the height plus 1/2 the base times the height. And we're going to get 2 plus 9 halves. We're going to get 13 halves. So if I define a new function, f hat of x, which is equal to 2/13, the absolute value of x on minus 2 to 3, this is now a probability density function. And I can ask all sorts of questions associated with it. It's still the same picture here. That's a picture of f as well as a picture of f hat. It just so happens that the height right here is 4/13 now, and away we go. So if I ask any question, like for example, what is the probability that 1 minus 1 is less than or equal to x, which is less than or equal to 2, well, you just convert it to an integral. Now, the support is where this function is non-zero. We can express the integrals in minus infinity to infinity, but in general we will just suppress that and say, well, the only resulting integral that has any meaning whatsoever will be the integral from minus 1 to 2 of the absolute value of x dx. And so now it is useful, whoops, forgot the 2/13 in front. It is useful to remember that the integral is defined by two different functions, one on the left of 0 and one on the right of 0, so I'll split it into two pieces. And so this will be the integral from minus 1 to 0 of absolute value of x, plus the integral from 0 to 2 of the absolute value of x. And this will be 2/13 times the integral from minus 1 to 0 of minus x, plus the integral from 0 to 2 of just x. And at this point, we reach two integrals that are nice to do. 2/13 integral of minus x will be minus x squared over 2, evaluated from minus 1 to 0, plus 2/13 x squared over 2, evaluated from 0 to 2. And now both of these evaluations are quite simple. 2 minus 0 will be 2, so we get 4/13 for that. And this one over here will be 0 minus minus 1 will be 1/2. It'll be 1/13. Y will get 5/13. So the probability that the random variable takes on a value between minus 1 and 2 is 5/13. So it's fairly straightforward, simple calculation. Well, if we can do that, let's take the same function. And let's calculate the expectation of the random variable. In other words, the mean. Well, that's not so bad. That's the integral of x times the absolute value of x on minus 2 to 3 dx. Now, once again, we want to understand how the absolute value of x behaves, so I'm going to break it in two pieces. 2/13, the integral from minus 2 to 0 of minus x squared plus the integral of x squared from 0 to 3. Now I'm dropping the dx's. I've replaced the absolute value of x by its associated component, and then we'll get 2/13. Integral of minus x squared will be minus x cubed over 3, evaluated from minus 2 to 0, plus x cubed over 3, evaluated from 0 to 3. And now these evaluations, the reason the minus is in there to create a positive, 0 minus minus 8/3 will be 8/3 plus 2/13, 27/3, or 9. And here's our solution. Now, we can continue. It usually is the case that if you want to calculate the variance or the standard deviation of the variable, that it's very reasonable instead to do the expectation of x squared minus mu squared, which we just calculated, so this becomes a single additional integral. One almost hardly ever proceeds forward onto such a variance without having calculated something before. So now, since one of the things I really harped on and liked was the moment generating function m of t, it seems to me that we should be able to do the same process, the expectation of e to the tx with continuous functions. Now, unlike the discrete case, you have to be able to successfully integrate these things in order to calculate the moment generating function. And you have to know the interval in which they exist. Now, probably the most easy moment generating function to calculate initially is the moment generating function on some finite support polynomial. It's a question of, can you integrate x to the n e to the tx? Now, you should know that this is a question of parts. And so if you're going to do this type of integral, you're going to have to be able to remember how to do parts. So let's do the continuation. Let's do that moment generating function, that function we were just working with, f hat of x, which is 2/13, the absolute value of x, on minus 2 to 3. What is its moment generating function? Well, it is its DNA. It has everything about it inside of it. Let's do a calculation. So, by definition, the moment generating function is the expectation of e to the tx, but the expectation of e to the x is integral of e to tx, absolute value of x, 2/13 from minus 2 to 3. And dx, which is the 2/13, the integral from minus 2 to 0 of e to the tx minus x, plus 2/13 integral from 0 to 3 of x e to the tx. Now, in order for us, I should put the dx's in there. In order for us to do either of these, you need to observe that we need to have the integral of x e to the tx. So let's just set this aside and let's do the integral of x e to the tx dx, which is not really a rocket science integral, but got to remember parts, so we'll go over it. So I'm going to let u equal x dv equal e to the tx dx. So du is dx, and v is 1 over t e to the tx. Integral of e to the kx is 1 over k e to the kx. So this integral then is uv x over t e to the tx minus the integral of v du 1 over t e to the tx dx. But this integral we've just done once before, x over t e to the tx minus 1 over t squared e to the tx. So that was not a terribly hard integral to do, and so integration by parts is readily available to us, and so now we can pick up here and we can say, wait, now I know this. Each of those was x over t e to the tx. So I'm going to put the 2/13 in front, and 1 is a minus x over t e to the tx minus, so that'll be a plus 1 over t squared e to the tx. So that's the first integral. Now, that's with the minus having switched everything, and that will be evaluated from minus 2 to 0. And now the second one is the same one, but with a different order of the minus sign, x over t e to the tx plus 1 over t squared e to the tx, and this one has to be evaluated from 0 to 3. Now, it kind of gets hidden here what it's going to look like, but it's not so bad. So let's do this evaluation. The 2/13 is still hanging in the front. I'm going to plug in 0, kills that. It makes this one 1. So we get 1 over t squared. Now I put in minus 2, and a minus minus 2 will become a plus 2 over t e to the minus 2t. And minus 2 in there will be 1 over t squared e to the minus 2t plus minus. Yep. Now we'll put the 3 in here and we'll get 3 over t e to the 3t plus 1 over t squared e to the 3t. And now when you put in a 0, that one will go away. Minus 1 over t squared. And so there's this expression. It's got the powers of the exponent at the endpoints of the function. It's got some other t's floating around here. It's kind of complicated, but when it gets down to these moment-generating functions, it's not that hard to create moment-generating functions for finite integrals. You just have to be able to do some usual integration by parts. What's more fun is when we have an indefinite integral of the infinite type, where we have some function that goes down, and we have the ability to integrate that function from some fixed point to infinity, and the answer is less than infinity, so we get an answer. That means we can create a moment-generating function by dividing by whatever the answer is, and now we have a PDF whose area under the curve is 1. Now, selecting the right function isn't so bad. There's lots of these that you can do integrals with, but how many of them can you actually integrate the moment-generating function when you throw an e to the tx on it? Now it gets a little bit more dicey. So we'll start with a pretty standard one, the exponential function. We've already seen this, so let me put some random e to the kx with some constant in front as my starting f of x. And I'm going to start it at a value 0, make life easy, but I can easily start it at a. So I'm going to kill the function over here. And so the function is 0, up to 0, and then onward. So it's going to be this for x greater than equal to 0, and 0 for x less than 0. So we've got rid of that part that's non-useful. Now, we want this integral to actually equal 1. So when we integrate e to the kx, we get a over k e to the kx, and we have to evaluate from that from 0 to infinity. Now, it's really clear that k has to be negative, otherwise this is going to blow up on us. We've done this integral before in calculus. So how do we prevent it from blowing up on us? We have to have a negative k. So let's make k positive, but put the negative in there. Now when we put in infinity, that's going to go away. When we put in 0, we're going to get a over k with a minus minus. And so then it means we just have to put, to get this area of 1, we just have to put, a over k, so we have to just put k over a. So we just kill that, and here's a function defined on 0 to infinity, whose integral equals 1. So now we have a nice function to work with. Well, let's do its moment-generating function. So I have this f hat of x equal to k e to the minus kx on 0 to infinity. K is positive. So now the expectation of the random variable x is the integral from 0 to infinity of k e to the tx e to the minus kx dx. Now, just as we had seen when we did the series solutions before, these are not terribly hard to do if you recognize the algebra that allows you to complete it. The algebra here is pull the k out, write this as t minus k to the x power. This is still 0 to infinity dx, but now it's an e to the lambda x, whose integral is 1 over lambda. And we're now going to evaluate this from 0 to infinity. Now, we need to be slightly careful here. Why do we have to be slightly careful? Well, we want to make sure that this integral calculates. We want the limit to go nicely. Well, if we just require t minus k to be less than 0, then when we go to infinity, that portion will produce 0, and we put in 0, we'll get k with a minus front, t minus k as our answer. So this requirement is required for the moment generating function to exist so that we get an answer. Now, it turns out this form isn't terribly pleasant. Got too many minuses, so I'll put the k here, and I'll write it as k minus t. That seems to be more useful. But I would really like this function to have some nice properties. And it turns out that if I take a look at the expectation of this function, and I made a mistake here, I do apologize. This is the moment generating function, so that right there should have been e to the tx. I would like to know what the expectation of this function and evaluate it. Well, I'm going to use this m of t here and see what it looks like. M prime then, where t is the variable. Well, that'll be just k over k minus t squared. Put a minus in front, is the power 1. Now we're going to evaluate this at 0. And so we'll get minus k over k squared. Did I do that right? Oh. Derivative had a minus in front, but the derivative of the inside is a plus. I forgot the chain rule here, so this is gone. And so we get 1 over k. It seems that writing our function with a k in here in this fashion wasn't the best way to write it, since my expectation is 1 over k and my m of t looks badly. So it turns out that this entire function here can be redefined if we just use a nicer variable. So what I'm going to do now is I'm going to redefine my exponential function. I'm going to choose it to be f of x equals, and instead of using k e to the minus kx, I'm going to use the standard book uses 1 over theta e to the minus x over theta. Now what I've done from here to here is I've simply switched in k equals 1 over theta. It's just a parameter change. Well, what does that do? That parameter change causes our moment generating function, which looks kind of funky. Remember, it was k over k minus t. Well, if I factor out a k out of the top and bottom, and now observe that we made the substitution that k equals 1 over theta, why, we get 1 over 1 minus theta of t. The moment generating function looks nice. And we also discover that m prime of 0 now is theta. So when it's written in this form, the exponential function has some kind of nice properties. Namely, it looks a little harder to write, but the moment generating function is nice, and so is the expectation of the function.